There's nothing you can do that can't be done. Nothing you can sing that can't be sung. There's nothing you can know that isn't known. Nothing you can see that isn't shown. Welcome back to the Applied Deep Learning course. Today we're going to take a look at transformers and how they change the field quite dramatically in the way how we think about sequence modeling nowadays. But before we do that, let me quickly recap from last week's lecture. What is the relationship between the input and the output of an autoencoder? It's the same. At least we try. So an autoencoder takes something as input and tries to reproduce it as the output. And if it doesn't manage to do it in a good way, it will be penalized with the reconstruction loss. What are the two main blocks for autoencoders? It's on the one side the encoder and on the other side the decoder. The encoder takes the image, tries to find a different representation of that input, and the decoder then tries to take that representation and reconstruct the original input. What can you use autoencoders for? Well, there are many things you can use autoencoders for example, for unsupervised pre-training, similarity detection, anomaly detection, and many other applications. How are variational autoencoders different from standard autoencoders? So the variational autoencoder uses a special probability distribution in the middle, in the latent space, in those bottleneck of the autoencoder. So instead of using direct values, it predicts a probability distribution with a certain center and variance, and it samples from that probability distribution that it tries to learn to obtain values for the decoder. What does the Kullback-Leibler divergence measure? It measures the difference between two probability distribution and sums it up in one number that tells us how good we're doing if we're approximating one probability distribution with another probability distribution. What are the two main blocks in generative adversarial networks? On the one hand, we have our generator that tries to produce samples that look as realistic as possible. On the other hand, we have our discriminator that tries to figure out whether an image is from our real distribution or whether it's a faked sample that was generated from the generator. These two blocks play against each other, and everyone, like the generator, tries to fool the discriminator, and the discriminator tries to be as good as possible in figuring out whether this is a real sample or a fake. And by letting them play against each other, you can actually train a good generative network that produces samples that at least fool the discriminator. So now to today's topic, transformers. When you think back a few lectures, we talked about sequence modeling with deep neural networks. And one of the most popular choices for this still today is using recurrent neural networks. Most of the time with some sort of encoder-decoder architecture. So imagine that we have a task like language translation from French to English. Then we have a sentence that can have an arbitrary length, and we want to process it and then produce a sentence in the other language that has the same meaning, but of course is now in a different language. And one way how we can do this with such an encoder-decoder architecture is that we take the words, the samples from our input sequence, process them one by one in a recurrent neural network until we arrive at the context, at a hidden state that contains all of the contextual information that we need and that we have available about that input. And given that context C, we use a second block, the decoder, that generates one word after the other in the target language until it finally reaches a point where it says, okay, this is the end of the sentence. And this kind of sequence modeling with recurrent neural networks has a couple of downsides. So first of all, you already realize we have to process this sequentially. We take one input, we feed it through our recurrent network, and given that it's a recurrent network, it feeds information back to itself. So the next time step, the next word that comes in, is depending on the result of the previous time step. That means it's gonna be really slow. We need to process this word by word. And also training this is often super expensive, and when you take a look at how this is most commonly done, it's not by full backpropagation through the entire sequence, but truncated backpropagation through time, because it is so expensive to kind of perform an update step if you go all the way back through the entire input sequence. Given this sequential nature, we have the issue that we can't really make use of parallel computing. We're depending on results from the previous computational step. So this is a severe bottleneck of these recurrent models. And last but not least, long-term dependencies are problematic. Because when you take a look at this image here, the information that we know about the sentence, all of the information must be stored in this one context vector that we have in the middle. And from there, the decoder has to kind of figure out how to process that context information. And that is a big challenge for the network to be able to push and squeeze all of that information into that representation in our hidden state. Kind of seeing one word of the input sequence and then referring back to it at a much later time is also for recurrent neural networks really challenging. So this long-term memory, when you think about it, we can have kind of different ways how to tackle this. If we have a CNN, typically we have a fixed size window. We can use CNNs for sequence processing just as recurrent neural networks if we have, say, a fixed window size. Say we have 4 words, then we have kind of 4 words that we always see at a time, and then we can process that. With recurrent neural networks, we get a bit of a longer reference window where the network still remembers some of the information that it saw before. And with LSTMs, we were actually able to extend this to an even wider reference window where we can see and understand much longer parts of our input. For example, here, when we were reading the sentence, "When I woke up, I saw the most incredible thing that I've ever witnessed. I tried to understand what was happening, but at the moment, I just stared blankly at it." So, thinking about this word "it," at the very end, what does it refer to? So even if we have this long reference frame that LSTMs give us, it can refer to something that we saw much earlier, in this case, the most incredible thing. And if we're outside of that reference frame, of the reference window that we are able to access information on, we have a hard time understanding the context of what it refers to. So the idea would be, can we extend this and kind of have the entire context available at the same time? And this is the idea that transformers employ. So with transformers, we process the entire sentence or the entire input sequence in one swoop. So what is a transformer? A transformer is an architecture that is based on an autoregressive encoder-decoder architecture. And you already see that this encoder-decoder idea sticks with us for a long time because it's a really interesting and a powerful idea to process something into a different representation that is more efficient and then generate something else out of it. And what's with this autoregressive So autoregressive means that if we produce one word in our output, we feed that back into our model. Then it will be autoregressive. So the idea is, it started basically this idea of transformers with a paper called Attention is All You Need by the Google Brain team. And on a high level, how this works is that we take our input, we run it through an encoder, we produce, again, latent space representation in this abstract continuous space that holds all the learned information from our input. And then we use the decoder to produce our output sequence. And one key ingredient that you can find in transformers that really drives this to the level that it performs is an attention mechanism. So before we get to this attention mechanism, let's dissect this figure that I'm showing you here and try to understand all of the individual components that went into this design. And we're going to start with the input embedding and the positional encoding. Neural networks do not understand words. They do not understand images. They understand numbers, vectors, matrices. And given that we have, say, a language in like a sentence given in a certain language, like French, we have to find a suitable representation for that sentence. And this input embedding is exactly doing this. It's going from a word in an input language to another representation that the machine can actually understand. There are different ways how we can get from an input to this representation. We can use language embeddings that are already pre-trained, like word to vec. For images, we can use a standard convolutional neural network backbone to extract features that are then fed into this network. The second part is the positional encoding, which is necessary because as opposed to RNNs that process our input word by word, sequentially, we're now feeding in our entire input sequence at once. And given that we feed this all in one swoop, we have to add this positional information because it is important at which position of the input sequence a word appears. So the positional encoding does the following. We're adding contextual information of the position to our input in the following way. We have the embedding as an example here now. We have the embedding of the word dog. So it gives us these 4 numbers. And what they propose in the original paper is to use 2 functions, a sine and a cosine function, with alternating frequencies, and alternating between sine and cosine, you compute an additional number here. Why are they using this? Because it has some nice properties for computing and differentiability. So it's a sane choice, I would say, to use that function, but it's by far not the only function that you can use to encode some sort of positional encoding. And given that we now have this sine and cosine functions that we can compute additional numbers from our input and the position here, we add this and then we obtain the embedding of the word dog of our input with that contextual information. That contextual information is now part of our input. Now we come to the most exciting part of transformers, attention. We're gonna see that attention appears in our network actually 3 times, and I'm gonna start with the first multi-head attention here in our encoder. So attention and self-attention basically tries to answer the question, at what part of our input should we focus on? So it captures this contextual information between elements, how they interact with each other. And here's a really nice figure that I actually want to bring up on the interactive website. So we're now on this wonderful website that has an animation of an attention, of a learned attention. And what we're seeing here is that it learned to translate French to English. And as we can see, certain words relate to other words in a strong relationship and with others in a weak relationship. For example, the word zone refers to area with a kind of strong relationship. Again, economic, economique, European, well, that's pretty obvious. But we can also see some interesting insights. For example, the word la, French, the article, is depending on the noun. So it's not just relating to the word the, but also to area, because depending on the gender of the noun, we have to use a different article in French. So we can see all of these nice interactions between words in our input sequence and words in our output sequence. And this is what attention is really all about. Tell me how things relate to each other. With self-attention, the word we're adding here is self, we're actually associating each word of our input sequence with itself. That's why it's called self-attention. So how this works is that we have a sentence, for example, the big red dog, and then we're trying to figure out how each word of our input relates to all other words of our input sequence. In this example, we could come up with attentions that look like this. The question is, how do we get there? How do we get these attentions? Because that obviously seems to be the tricky part, to compute these attentions. If we have them, we can do a lot of wonderful things with them because we now understand how words relate to each other. How we implement this is by first conceptualizing this as a retrieval problem. So a retrieval problem we can formulate by three inputs: a query, a key, and a value. Think about when you go on a search on the web for something, the word that you type in would be our query, and then we have key-value pairs. So the key identifies the thing that we're looking for, and the value is the underlying number that we're really interested in. And for our attention mechanism, we can implement this kind of concept by a series of matrix multiplications. So coming back to this Q, K, and V, the query, the key, and the value, you can think of it as the following. We have a query, which is our input word, like one word in our input sequence. And then we have the key, which are all the other words in our input sequence. And the result that we want to obtain is a score that ranks kind of how much I want to relate all of these other things, and then fuse that score with the actual value of that word to be further processed. So what we're doing is we're taking our input sequence and we're splitting it up into three parts: the query, the key, and the value. Given that we're doing self-attention, we only have that one input. And these linear layers here actually learn the weights how to kind of get to these three parts: the query, the key, and the value. So what we're doing here now is we're taking the query and the key and we're computing the dot product between them. And the query and the key multiplied with each other gives us a set of scores, a matrix. This is maybe something that I should add here. Given that we compute this for the entire input sequence, we're not feeding in one single value, but we're feeding in a vector and we're getting a matrix of scores here. Now we have something like this. And what you can see here is how each word relates to each other word of the same sequence. And unfortunately, that multiplication can explode quite easily. That's why we're typically normalizing it to kind of stabilize our gradients. So we're dividing this by a number to get scaled scores. And ultimately, those scaled scores we feed through a softmax function that computes normalized values that resemble a probability distribution and highly rank, give us high numbers for things that are related to each other, and low numbers, ideally 0, if they're completely unrelated to each other. Now we have the scores that tell us how much each word is related to each other word, and then we can take that score and multiply those attention weights with the value, which is, again, our input to obtain the actual output. And one more thing for this attention block here is that, unfortunately, if we use this self-attention, the network pays a lot of attention to itself, to the words of the, pays a lot of attention to the word the. And given that we don't, well, I mean, it's obvious that the word is related to itself, but it's not really useful. And to alleviate this problem a little bit, we replicate the attention layer multiple times, and then we take all of those weights that are being produced and average the results. And this reduces this problem, and given that we now have not one attention layer here, but many of them, we call this multi-headed attention. Coming to the next attention block, which is the masked multi-head attention in our decoder, that I really want you to understand first. So when we're processing the output sequence, we're basically doing something very similar. We're also trying to understand, in, say, the English language, how words relate to each other. The problem is now that we're producing outputs, and, well, for training we have already the output sequence that should be produced. The problem now is that if we feed the network all of the information of the target output representation of the output sequence as input, it will just learn to kind of point to the next word in our sequence. And what we have to do now is we kind of have to cut out that part of the information. And given that we, again, feed in our entire sequence, this becomes a matrix where we have to cut out all the words that appear later on in our output sequence. So when we're starting the sentence "I am fine," we shouldn't have access to the word "I." So all of those words from our output sequence here will be omitted. When we have access to the word "I," we can learn how it relates to the start, what it saw before, and the word "I" itself. When we're at the word "am," it can access all of the information it saw before. So we're only allowed to take a look at the past. How do we do this? We have our scaled scores that we compute exactly in the way that we did for our encoder, and we add this so-called look-ahead mask, which is just -infinity for the right top part of our matrix. And if you sum these up, you get those masked scores where all of the right top part of our matrix is -infinity, and after normalizing this, those will become 0, which is exactly what we wanted to have. Now, we're kind of enforcing that the word, like when we're producing or processing the word "I," we're only paying attention to everything that came before and not that comes after. Now, there is one last attention block that we can see in this model, and that is now the secret source that connects these two things. So we have our input that gets encoded in a meaningful way. Then we have our first attention mechanism, which says how words relate to each other. We go to this hidden representation, and then we do the same for our output sequence. We also go to this hidden representation, and now the third multi-head attention here is the connection between those two representations. So as opposed to the input and output attention blocks here, this one is being fed information from the encoder and from the decoder. And here is where all of this sequence-to-sequence alignment between those two sequence types actually happens. There are a few more blocks here, but basically we already have the full model here. So we also have 2 feed-forward and normalization blocks here. What they're doing is basically transforming the output of the attention to a vector format that is digestible by the next block. And this allows parallelization because all input words can be passed in at the same time, because now these attention blocks are independent of each other. So these are just additional blocks that we put in place here to be able to process this in a better way and to extract maybe additional information along the way. And the last things that we can see here is the softmax and linear output. Maybe one thing I should point out before that, you can see the left and the right blocks are enclosed in gray boxes where you have an n times before. So the network that they're proposing is not just one pass through this multi-head attention, normalization and feed-forward, but actually 6 of them that are stacked behind each other, and then we feed that information to the other side. Similarly, the decoder is also repeating that process. Now, we have basically all our blocks except the linear and softmax things at the output, but those 2 blocks is something that we've already seen in other neural networks in a way that the linear layer is somehow producing or processing our data to make it more meaningful to process. In our case, we can use that linear layer or a fully connected layer to expand the dimensions to our vocabulary size in our output. Say, if we have 1,000 words, we would produce with this linear layer our 1,000 outputs. And then the softmax, as we know, is for classification, where we try to come up with something that the humans can interpret. In this case, it's going to be the probability, the most likely of the most likely word that should come next, given that input from our input sequence. And that gets fed back into the network, and then we're off to the next word. While this was the initial architecture of the transformer, there are some variations that became really popular and that you will probably encounter in the future. First up, we have the encoder-decoder. I would say it's the standard thing that we've just seen before. We have on the left side here the bidirectional encoder without masking, where all inputs are connected to all other inputs. And then we have our autoregressive decoder on the right-hand side, which is connected with the encoder through the cross-attention mechanism. This architecture is best suited for machine translation or text summarization. Now comes another variation of this, which I think is really interesting, which is the encoder-only architecture. In this case, we only take the left part here. We take the bidirectional encoder without masking, and we basically stop there at the end. And what we get is a dense embedding. And this is often trained through some unsupervised learning, for example, like next word prediction. And this dense embedding that we get here, we can then use for some downstream tasks like text classification or named entity recognition by attaching a certain classification head. So typical examples of the encoder-only architecture are Bert or Roberta. Finally, there is the third type that we have, the so-called decoder-only architecture. In this case, we only use the right-hand side, what we see here. Instead of the encoder with an attention mechanism, we only use a tokenization and a positional embedding, and then directly make use of the autoregressive decoder with the masked attention to generate our outputs. The most popular example of this architecture is the generative pre-trained transformer, or short GPT. Keep in mind that this figure is not 100% accurate in this case, because for the decoder-only architecture, we usually do not have the cross-attention mechanism between the encoding part, which
In this case, it would be only the tokenization and positional embedding and the actual decoder here.
Transformers have become state-of-the-art for many tasks from the realm of sequence modeling. But interestingly, it's not limited only to natural language processing, but has also transferred to other domains. And one domain would be object detection. We've already seen object detection in the past with convolutional neural networks. Now, let's take a look at how we can do object detection with transformers. When you think back about how we did object detection a few lectures ago, I told you that state-of-the-art models for object detection use the following. So basically, all of those models that claim to be state-of-the-art for object detection employ some form of deep convolutional neural networks. And we can formulate the problem of object detection by basically two ways. One way would be that we say we formulate this as a surrogate regression and classification task. What that means is we divide our task into two subtasks. One is give me appropriate regions, those surrogates, that I should take a look at. So that would be the first task. And the second task would then be, given those regions in our input, I try to identify which ones are interesting and kind of ruling them out and classifying what is in those regions, and ideally also maybe refining them a little bit to get even better results. And we've seen this with fast RCNN, which was a milestone for object detection with deep neural networks in such a way that it was the first time that we were able to train one convolutional network that jointly learned how to do this region proposals and the classification and bounding box regression at the end at the same time. And in many fields, fast RCNN still, or for many problems, fast RCNN still is a very solid baseline that you can go to and kind of try this first, and then maybe try a few of the more advanced kind of detectors that were developed afterwards. There are also a couple of ways how you can get rid of this proposal and kind of have a dense grid of proposals. We've seen this with one-shot detectors, but basically the idea is the same. But instead of having a sparse set of proposals, we're then having a dense set of proposals. But still, we're formulating this as a surrogate regression and classification task. The other way how we can do object detection would be by formulating it as a segmentation and clustering task. So we kind of go bottom up. We try to extract pixel-wise information. We classify each pixel of our input, and then we can group them into connected regions that ideally depict the same object. That would be also one way how you can do object detection. The problem with both of these approaches is that many of them rely on hand-designed methods. For example, the anchor generation for fast RCNN requires a set of hyperparameters that we as developers have to specify. How big should these initial proposals be? Kind of what aspect ratio do they have? How many objects should we try to predict? All of these are hyperparameters that we have to design ourselves. There are ideas how we can eliminate these things and kind of also learn how to extract proper anchors. But initially this was entailed by a lot of fine-tuning these hyperparameters on our own. So for example, we had to, what we see in the right top here, compute the probability distribution of the shapes of our objects, and then we could cluster them to find good set of statistics for our box proposals. The second problem that we have with many of these methods is that we need some form of maximum suppression. If our network is allowed to produce predictions that are nearly duplicates, like this dog, we are seeing 3 boxes that are being predicted. we have to kind of consolidate these boxes. Of course, there are not 3 dogs in that image. So we have to figure out which one of these boxes is the most likely one, and non-maximum suppression will be one way of eliminating these near duplicates. And for those bottom-up approaches, one common challenge is how to handle fragmented objects when you want to cluster your pixels together. If like one pixel over here and one pixel over there belong to the same object and they're not connected to each other, which is kind of challenging. And finally, maybe one more issue that could be hardening this problem of using this segmentation and clustering algorithms is, what if a pixel does not uniquely belong to a single class? If you have a box, boxes can overlap. If you have a single pixel and you just classify it to one output class, you're out of luck. There are again ideas how you can predict multiple labels for a single pixel, but those are really difficult to kind of train. Or maybe they're not that difficult, but at least they are present another layer of problems that you have to deal with. What we ideally want is a direct prediction of our bounding boxes. We want to feed in an image and we want to get a set of boxes. And the detection transformer is the first, to the best of my knowledge, the first paper that proposed such a model where we feed in an image, run it through a transformer, and then directly get a set of bounding boxes and class labels. So it's an end-to-end approach that gets rid of all these hand-designed mechanisms for anchor generation or non-maximum suppression, and it employs a really clever thing which is called this bipartite matching loss to kind of make sense of what those output boxes that are generated, how they relate to the actual boxes in our input image. It contains several blocks. The first block here is a standard feature extraction network, for example a ResNet 50, to go from our input image to this latent space representation. And when you think back about transformers we saw before, that would now be our input embedding, which is now a ResNet 50 to get something the transformer can digest. Let's go through this model from the end to the beginning. We start off with the bipartite matching loss. So the challenge is when we formulate object detection as a direct set prediction problem, how do we determine a unique matching between the proposals that the network generates and our ground truth set of bounding boxes? Because ideally we want to have a unique assignment here, and it shouldn't be depending on the order of how elements appear. So what they propose is that they search for a permutation that has the lowest pairwise matching cost. So we have 2 sets and we're trying to find the permutation of these elements here that have this that have the lowest costs here. So they take into account both the classes, the class prediction, as well as the similarity of the bounding box. And they can actually compute this efficiently by using the Hungarian algorithm, which is a combinatorial optimization algorithm that solves the assignment problem in polynomial time. And this is an assignment problem where we want to assign one element of one set to elements of the other set. How do they do this exactly? So they kind of try to minimize this matching loss. And the matching loss, as I said, takes into account both the probability or the class labels, so the first thing, the first part here, and the bounding box. And maybe I should point out the difference to how fast the RCNN is doing this. So for fast RCNN, we're also getting a set of boxes that it predicts, and those are running first through a non-maximum suppression to kind of eliminate all those duplicates. And then what we're doing is we're computing the intersection over union between all box pairs, if you want. And then we kind of order them by how well they overlap with each other. And the pairs that match with the highest intersection over union then are being produced in our output. So coming back to this bipartite matching loss example, given that image here, we have like two birds, and our algorithm predicted a third object in the right top of that image. For example, it said, well, there is a cat over there, even though there is no cat. What we have is now our set of predictions and our set of ground truth boxes with our class label. So the first thing we see here is that we have to have a fixed set of maximum predictions that we're allowed to produce. And if there are no more elements in our input, then we just pad those objects to always have a fixed length set here. And then our algorithm would try to find an assignment that makes the most sense, that has this lowest loss in this pairwise matching loss here. The interesting thing now is that it takes the global loss into account, because it tries to match all those elements from the prediction with all boxes from the ground truth, and tries to find the assignment that looks best globally, and not just having two objects have the highest IOU, therefore you match them with each other, but trying to find a more sensitive way of matching them. Now this, how to compute this is the following. This loss that you're feeding into their Hungarian algorithm is first the standard cross-entropy loss for the classification label. Like, we know this, if we have classification, the standard cross-entropy loss can be used to compute this. And the second part is for the loss for the bounding box, with an additional kind of toggle where we say if an object is of the type no object, because we padded our set, then we don't want to generate any loss. So we have this additional multiplier here that disables the loss computation for all other boxes. And they additionally also employ something really interesting here. So for the loss between the boxes, they split it up into two parts. One is what we already know, this intersection over union, which basically says how well one object overlaps with another object and gives us a single value. This is also called Jaccard index. So if you come across that term, maybe you're familiar with it. But they say, well, maybe this scale invariant thing might be helpful, but we should also take the scale into account, because for smaller objects or for bigger objects, this intersection over union kind of can be unfair. So if you have a large object that is like slightly shifted to a different location, it would get a quite high penalty from the intersection over union loss. So what they add is the second part, where they say, okay, this second loss term here is scale sensitive, to kind of make up for this. And they actually have introduced additional hyperparameters here, this lambda IOU and lambda L1. And they basically used for their experiments 2 for that first lambda and 5 for the second one. But they also experimented with different values. So those are just 2 additional hyperparameters that we have to deal with when we're doing this sort of object detection with transformers. So that's basically the bipartite matching loss. Let's go back to our full picture of this architecture. So now we understand how the network is able to match the set of objects that are being predicted in the output with the set of objects that are in our ground truth annotated data set. And let's dive into the kind of inner functioning of this transformer encoder decoder, the kind of black box that is really enabling this transformation. So it's very similar to the transformer we've seen before for natural language processing, but instead of feeding back predictions and predict boxes one box at a time, as we were doing this with sequence models, all boxes are predicted simultaneously. And how do they do this? They have this so-called object queries in their outputs, in the decoder, that are fed into the transformer, and for each of these object queries they produce one output proposal or one output prediction that is then classified and refined with a final feed-forward network in the end. So the number of objects that we're able to predict is equivalent to the number of object queries that we feed into our transformer. So the encoder basically just learns to extract interesting features and kind of learn where to look in the image with the attention mechanism. And then the decoder tries to understand, okay, when I look at that part of the image and I have a query that says, look at that part of the image, I produce a box that will look at that part of the image and say that's probably maybe a bird. So in detail, the architecture is very similar to what we've seen before, in that we have our encoder on the left side with a multi-head self-attention, where we have again our values, key and query, and then this normalization feed-forward network. And on the other side, it's exactly the same, with the only exception that we're now using these object queries instead of our output sequence. And at the end, well, we're not doing classification, so we're not employing a linear layer and then a softmax layer, but we're actually having these feed-forward network, like two heads. And of course, for the classification, we then use softmax, and for the bounding box, we do some sort of regression. But basically, it's just another transformer with images and these object queries. What are these object queries? You might ask yourself. Object queries are actually learned as well. And it's a really interesting idea of that the network is able to sort of ask the decoder different things. And for different questions, you get different answers. And it's an idea that is similar to guided anchoring, where we also learn this kind of where to look in our input image. And what you can see here is a visualization of all box predictions of all images on the COCO 27 validation set. So in that example, they had 100 object queries, and they are showing this visualization of 20 of those. And you can see one green dot for a small box and where that box appeared. Red would be large horizontal boxes, and blue large vertical boxes. And it's quite interesting to see that some of these object queries kind of focus more on the center and say, well, give me small boxes and big boxes in the center, and other object queries are conditioned to look on the side and maybe only look for small objects on the left, or small objects on the right, or long objects in the center, and so on and so forth. When you visualize the decoder attention, you actually understand that this model of doing object detection with transformers is really powerful, in that it really understands the input image in a really nice way. For example, for these images where you have occlusion in your input, you can see where the network looks at. So it visualizes those with sort of heat maps, and you can see the back and the tail of the elephant, or maybe even the legs that are behind the first elephant. It still pays attention to these, so there was a high activation in the neural network to understand the extent of our elephant. Also for the zebra, you see that where it basically looks is the kind of the extreme outer parts of the zebra, like the ears, the legs, and even some of the, what I find really interesting is maybe the most interesting thing is this part here, where we see a leg, and obviously that leg could have two objects where it belongs to. So it could also belong to that blue zebra, but the network understood, okay, well, zebras don't look like this, that they have a small leg very far in the back here, but it actually belongs to that zebra. So I think that's a really interesting way of visualizing also the attention that these layers learn and understand whether your model is doing something meaningful or not. The inference code for this is, I would say, quite overseeable. It's pretty short, and you can try this. There are a bunch of implementations of this detection transformer networks where you can just play around and feed your own data to a pre-trained model and see how well it goes. So some of the strengths of this detection transformer is that it generalizes actually pretty well to even an unseen number of instances. So they had this nice visualization here where they just took one image and they replicated it a bunch of times. And even though the network never saw such an image, it can generalize this and say, well, there are, I don't know, 24 giraffes in that image. And it can even be extended to perform panoptic segmentation. And if you forgot what panoptic segmentation is, it's the most challenging part where we basically do the intersection of instance segmentation, where we say which pixels belong to which instance, and semantic segmentation, where we assign a label to each pixel in the entire image. So we also have to assign labels to all of the background objects. Basically, that's what makes this so difficult. Unfortunately, there are some caveats, so it's not that kind of perfect to do this for all sorts of tasks with object detection. So basically you have very long training scheduled. I think it's 6 days and 8 GPUs that they trained their model on. It does not perform very well on small objects, and it doesn't perform very well if you have a lot of objects. And this is very understandable. So if you get near to that maximum number of objects in your that you're potentially predicting, the matching becomes much more complex. That Hungarian algorithm has to compute way more combinations, so it kind of naturally degrades if you have a lot of objects. Say if you have 1,000 objects in a single image, which you can easily have if you're working on music scores, for example. But in general, it performs at least as good as fast RCNN, and I think it's a really interesting take on like another spin on object detection, but now with transformers. I think here you can also see in this left figure that the number of visible instances and the process of percentage of missed instances kind of goes up the more instances you have. So it kind of really works best if you have a low number of objects in your image. You can play around. The implementation is open source and it's available. I actually encourage you to play around with it, see if you can get some interesting ideas. And there are also, I'm pretty sure, lots of follow-up work with this initial idea of using transformers for object detection. So look out for these interesting new papers that are coming out on a regular basis. So transformers really have changed how we do sequence modeling and has significantly improved many problems like natural language processing and other sequence-to-sequence problems. And here are just a few examples of papers that came out in the last few years that, starting with this initial idea of attention is all you need, which is it's not just attention, it's also those normalization and other parts, but basically attention, like using attention for sequence modeling, have advanced this idea. One would be embeddings from language models, or ELMO, where we replace the fixed embedding with context-aware embeddings. And that makes sense when you're into language processing and you take the word stick. It can mean something completely different depending on where it appears in the sentence and what appears and what comes before and afterwards. So we need the context. It can be the end of a broom, but it can also be a verb. That means we should stay with something. So what they propose is to use, to replace this fixed embedding of, for example, word to vec with a context-aware embedding, where it also looks into the input sequence to figure out a more meaningful way to assign a value or embedding for that word. ULM fit is a process for fine-tuning language models for various tasks, and we're now able to do transfer learning for the sequence tasks in a similar way that we're able to do it for computer vision tasks, where we just train on ImageNet and then replace the head or replace the data set with what we actually want to train on. And that was also significant advancement here. BERT is an efficient way to pre-train transformers. And one of the ideas that they have in the paper is that they mask their input. So they randomly mask out words and then they ask the network, so please tell me what word should come in there. We have reformer, where we use local sensitive hashing for more efficient attention. The idea here being that this attention mechanism, if you think about the complexity of this, it's actually quite expensive. So if we have an input sequence of 100 words, the matrix that we're computing here of attention of one word to the other word is, so if n is our sequence length that we're processing, it's n squared, that matrix. And what they're doing is they're say, okay, maybe we should use some sort of local sensitive hashing to compute this in a more efficient way. There is an even more advanced version of this, which is linformer, where they even showed that you can reduce the complexity of this n squared to something that is linear, and the idea is that your self-attention mechanism, that matrix that we have, this n squared matrix, can be approximated by a much lower rank matrix, and that helps us to kind of make this computation much more efficient. And there are even some people who are going back to convolutions and introducing some really interesting ideas, like in this paper of lightweight and dynamic convolutions, where they're replacing this idea of self-attention again with convolutions. And the interesting idea here is that the convolution in their paper, the kernel is not static. So the kernel of how they process the input is now changing over time. So each time step, or basically, in other words, the kernel is time step dependent, which I think is a really interesting idea. There are even more advances from the field of computer vision, where transformers are also now becoming increasingly more and more popular. One idea would be to replace convolutions entirely with transformers. This approach is called vision transformers, and you can see it at the left bottom image here. Very simply put, what it does is it takes an image, it chops it into a number of equally sized patches, and then extracts features from those patches with a linear projection. Those extracted features are then fed into the transformer encoder, thus you can entirely remove the convolution here. Given that this has certain limitations, people understood, okay, well, if we use the same thing over and over, we have a couple of issues with those patches, like what happens if we have overlaps,
And that gave rise to the second approach here, which is called shifted windows in vision transformers, thus the name SWIN, shifted windows. And the idea here is that you're not only cutting the image into patches, but instead you actually form kind of a hierarchy, and you, like, depending on like the layer you are, you actually shift those windows and you scale them accordingly to allow the network to see and information to flow across boundaries of those image patches from the previous layer. Some other aspects that have been improved are, for example, the used loss, or what is also increasingly popular nowadays is to use the attention layers to visualize the network or some certain inputs to gain some kind of level of explainability from your inputs and try to get some information. Obviously, those couple of examples are just a glimpse at the advancements that have happened since the initial release of the Transformer paper a couple of years ago. Transformers are nowadays playing an increasingly crucial role in many domains, especially in large language models. For example, in GPT, they're using a transformer. So I recommend that you keep an eye open for advancements related to transformers, because they've come to stay and they will play an increasingly important role in many neural network architectures and many domains in the future.
Summing up today's lecture, we talked about transformers, and transformers are a really powerful model for all sorts of sequence-to-sequence problems like language translation or image captioning and so on. Transformers consist of an encoder and a decoder block, and the secret sauce for them is this attention mechanism that allows them to process the entire input sequence in one go and learn how one word of the input sequence relates to other words of that input sequence. This is actually called self-attention and kind of is exactly what I just told you. There are many current advances, as you've seen, like how to improve pre-training, how we can do transfer learning, how we can compute this self-attention mechanism in a more efficient way, ideally with a linear algorithm, linear time and space complexity algorithm. They can actually also be used for object detection that we've discussed in the end now, by formulating it as a direct box prediction problem and transforming a set of object queries. That was this idea of not having an output sequence, but object queries that learn kind of where to look in our input image into unique object boxes, these bounding boxes, and had this Hungarian algorithm of this bipartite matching loss, where trying to find a unique assignment between sets of boxes. This concludes today's lecture. I hope you found it interesting, and I wish you a wonderful day. Stay safe, and I'll see you next week.